So sorry, I didn't notice that there was a small crest. So that's why I didn't understand. Was everybody was like this? I was in my mood and and. Okay, so as a tutorial, it is concerning solar pumping. But if you have followed my previous speech, I said that solar pumping is the more simplest solar installation. So I will present the solar pumping, how it's designed, but there's no more difficulty. There's no difficulty on such a thing because there's only solar panel, pump, and that's all. So in terms of tutorial, I will present you an application, okay, what is the principle, but I will prefer after that you work on a more difficult design. So it is solar plus battery, okay? That is the reason why we print and you... did you send the mail to everybody? Okay. So, and it is more difficult because you have to design the solar PV and then also to design the battery, to choose the battery and to see how to connect them, okay? So if you agree, I will speak about that. And if we didn't have time to finish the tutorial that I proposed to you, we will start tomorrow morning to finalize it, okay? Like this tonight, you can have also time to look at my lecture, how to design and to come back tomorrow to finalize this. Okay, so solar pumping, it's very simple, but could be very essential in some place where there is no grid and where there is need to manage the water. Here, sorry, it's in French, but I can translate. First, for solar pumping is to identify what are the needs, okay? It could be used for fire, when there is fire, it could be, but it could also be for the given some resource, water resource for village, for human, for animals, for agriculture. So this is in French, but you will fully understand. So for human, in order to survive, it is a need of 5 liters per day, okay? For the conventional living condition in Africa, it is 30 liters per day, sorry. For animals, of course, you have to identify also what are the needs. For the cow, it's 40 liters per day. For goat and lamb, 5 liters. Horse, donkey, camel, and agriculture also. So finally, the principle of design is all the time the same, to be able to identify the need and then to answer to the need thanks to solar energy. So sugar cane, wheat, rice, so you need for agriculture a large amount of water. So this can help you to design. You need to identify what is required in terms of quantity. So the principle is quite simple. You are pumping in a river or in a hole in order to store the water in a tank, okay? And so the main issue of the PV will be to bring electricity to a pump, okay? And so the whole problem is to clearly identify the amount of water per day that you have to pump and to store. So and so the distance where you have to bring this water, there is two things which is important. It is the flow rate, okay, for a day. You know that, for example, during 5 hours you will be able to pump during the day. So it gives you the flow rate in order to fill the tank, okay. And the other thing which is important, it is what is the distance, what are the tubes to bring the water from one point to another. And what has to be done is to evaluate clearly the pressure loss along the path of the water. Okay, so there is two things. First, you identify the quantity of water per day. Then, depending on the location, you look at the climate. Is it a very sunny local area? If it is very sunny, you can say, okay, I will pump during 5 hours. So it gives you an idea of the flow rate to fill your tank. Then, regarding the distance between your storage to the way to pump, you have to evaluate the pressure loss. And so with these two parameters, there's two main parameters: flow rate and the other parameters for pump, you know, it is manometric eight. Manometric 8. So the manometric 8 is considering the difference of altitude plus the pressure loss. Okay, if you forget that, you will never reach the top of the tank. Only if you just consider the difference of altitude, you will never reach, because pressure loss, well, it is here at the aspiration. It is all along the circulation. It is, we call that linear pressure loss because there's friction. But the more important is singular pressure loss. When you have a change of direction, you are losing energy finally, and so it's essential to consider all. So these two parameters are essential for the choice of the pump. Okay, and there is many different pumps. So I repeat, first to identify the tank, then identify the volume, the time of sun, time for pumping, it gives you the flow rate. You have to also evaluate the path, and so. Okay, there is many different ways to identify the pressure loss and the manometric 8. So manometric 8, as I told, it is HM here. It is difference of altitude plus pressure loss. Pressure loss is not expressed in this, it is written here in meter equivalent of water column of MCE. MCE column of water. I don't know if you have made the hydraulics. You have made hydraulics? Okay. So you can formulate the whole energy in terms of altitude. So this potential energy. Okay. So in one point you have this potential between 2 points. If you are losing, it is delta H, and this is proportional to meter. If it is water, we say that it is equivalent in a water column. So it's not the objective of the topic, but so it's to identify the difference of altitude is quite easy, but this has to be accurately done, but we will not spend some time on this. It is more hydraulic. Okay, but there is several. So for linear, so the friction with tube, the pressure loss is related to the length, of course. The more the distance of the tube is important, the more the loss is important. The diameter of the tube, and so the velocity power 2 divided by 2g. Okay, lambda is the linear coefficient of pressure loss. So it's related to the rugosity, the roughness of the tube. If it is plastic or if it is copper, it's different. Okay, if it is concrete, it could be concrete for big tube. The loss is bigger than plastic, for example. So this is the meaning of the flow characteristic. Is it laminar, turbulent, and of the roughness of the tube, viscosity of the liquid, but for us it is water. So the main principle, yes, it is to be able to evaluate that along the path. So for this tube, for this tube, for this tube, for this tube. Okay.
This one is a submersible pump, right?
Yes, this is a. I will show you different. So usually you have this or you have this, and it is two different kind of pump. But to show you, but yes, it is a submerged pump. Yeah. Okay. Okay. So first is linear, and second it is singularity. So this is also something that could be formulated like this. At this you have a singularity coef. So if you have a change of direction, if you have a van to open or to close, each different components on the path is a singularity. and so you can find easily, and when you choose an hydraulic component, the coefficient of loss, okay, which has to be applied like this. Okay, so this linear, this singular allow you to identify that. It is essential to identify that, to combine to the difference of altitude in order to have the good manometric height, okay? So the meter of column of water, is it clear? Do you have any question regarding that? So through this H of the pump, it is easy to come back to the power, hydraulic power. Sorry, it's equal, it's not different. So to become what I have meter here, it is easy to find what we have to do. It's to multiply by the mass. So the mass is the density of water multiply the volume flow. Okay, so this is mass flow rate. Okay, and gravity acceleration is missing. mgh. It's proportional to an energy, but as it is a flow, it's m divided by time, it's become power. Okay, so this is the hydropower that we have to provide to the water to take it from the hole or from the river to the tank. Of course, there is an efficiency between the engine of the pump, which is electrical, to the real power transmitted to the water. Okay, so for the pump, the electrical power is PE. So it's bigger than the hydraulic power. And you have here an efficiency of the pump. Okay, so it could be 80% of efficiency. There is several things that make a loss. It is a mechanical piece inside. There is some friction, so there is some loss, okay, by the work, and also efficiency of the engine by itself. Electrical engine is also eating a bit by Joule effect, so you are losing. So globally, this global efficiency take in consideration that compared to the electrical power of the pump, you have loss to provide to the water. Okay. So as soon as you have the electrical power, it's finished. You know the electrical power that you have to provide to your pump. Okay. It's clear? Some question? So you have different kind of pump. You can have some pump that are submerged. You have floating pump also if it is on a river. So typically it will be this kind of centrifuge pump that you will use if you are in this configuration. There are 4 types of pump for this kind of configuration. If you are submersible, it will be that kind of pump, centrifugal submersible pump, because you have many different pumps. You can find that, which is, I don't know if there is some in India, or you can, there is also in France some. It's also convenient when it is a windy area. You should take that better than solar. It's the same. And so it's yes, piston pump. So interesting. The previous also ancient was also the same. Okay, and so here you have the 4 different kind of pumps that could be used. And depending on the volume that you want to, the main 2 parameters is the flow rate, the volume you want to bring, and where you want to bring. So the 2 parameters is manometric and flow. Okay. Some pumps are very good for big flow, but small manometric properties. For example, when there is a flooding, okay, here there is a flooding in the building, you will put a pump directly here that a very small manometric height, but a very good capacity in flow, okay. The reverse, you can have weak flow, but big manometric height if you are going very deeply, but you can't have both. It's very rare. Then if you want to have both, you have to combine different pump. Put some pump in series or in parallel. Okay. If you are in series, it's to have what? Big manometric height or big volume? In series, so it's to have a big manometric height. You can put several pumps like this. In parallel, is to have a big flow rate with the same manometric height. So you can combine, okay? So this is the choice of a pump is like this. What flow and what manometric is the main 2 parameters to choose your pump. Also considering the way they are operating, the environment, if they are floating or if they are submerged, of course. This is not made to be submerged, for example. Okay. So this is characteristic. It's in French, but you can recognize the flow rate in liter per hour and the manometric, and you can see if it is centrifuge pump or volumetric pump, how they behave but so you can find that everywhere. So I was identifying that. We have compute that, the hydraulic pump power, okay, and determine, thanks to the efficiency, the electrical power. So I've made a direct link between electrical power and the global efficiency of the pump with hydraulic power as you remind. Okay. So quite simple to identify the electrical power that we need here. So for an example, the energy that is required per day, so it's approximation considering the G, the volumic mass, so this coefficient is coming from this. We can express the required energy per day, but you are able to identify by yourself exactly, not taking in consideration this. This is to considering that there is a full day of pumping, 6 hours or 7 hours. You take that in consideration to find that. The pump efficiency, depending of the pump, they are not so good. For example, the mechanical one that we see that with the wind turbine is not so good. But the interest is that there is no consumption, no electrical consumption. But you can reach 80%. So we can then throw this energy that is required per day to identify the peak power of our PV central. So it is energy required divided by the global irradiation of the place, okay, in kilowatt hour per square meter and per day. G is a jour. Okay. Then we deduce and also considering that there is a pump efficiency. Then you deduce the flow. You have the flow of the pump, and that's all. So when you have the peak power, then you can select a PV panel you want, and the way to use it. Is it clear? Of course, you have to design your grid and the size of the tube for the flow that you want. We avoid to have too much pressure loss, of course. We select the radiation for the bad day. It could be constant along the year, but if there is some months where there is a low level of irradiation, you choose that for designing your pump or your system, because it's important to have water which is necessary all along the year. So as an application, Ouagadougou is in Africa. The estimation, so when you look at is it for agriculture and so on, is 20 cubic meter per day. The difference of altitude, so probably it is in a hole, okay, I don't know, remember, so it's not in a floating pump, it is underground. So 30 meters. There is 100 meters of tube. Global horizontal is around 5.2 kilowatt hour per square meter per day in December. It is the worst month. The efficiency of the pump is not so good. For these pumps that are emerged is 30%. The energy required per day is 1,635 kilowatt hour per day. Then you deduce the peak power, considering the efficiency of the pump. You will have to install a bit more than 1 kilowatt peak. Oui, for the unit, it's French unit. This in French mean crête, but it is the same as peak. So you can find both kilowatt C or kilowatt P. And the flow of the pump is 4 cubic meter per hour. So that means that it will operate 5 hours. Because we want, so consider 5 hours of run, of operating. There was only 1 meter of loss. Okay, so it's not bad due to the different So when we have the peak power, then we have to look at different PV panels that we find on the market. Okay, so if, for example, we find Siemens PV or Voltec Solar PV of 1 square meter at around 200 watt, okay, you will put 5 panels to reach your peak power. Okay, it's better to oversize than to be a bit down. So the photovoltaic installation that is identified is for 1 kilowatt peak. The cost is quite. I think now the cost of this should be more around 2,000. This price is a bit higher. The maintenance, so it's important also to the cost to take in consideration maintenance. Okay, maintenance here quite simple. It is related to the pump or to the PV panels. Okay, there is no battery, there is no electronic device, or so we said that it was an estimation of the maintenance cost, and running 20 years, we didn't have this aspect about this coefficient. If I have time before the end of the week, I will show you the formula about that. But so it's an estimation of the cost per cubic meter to evaluate the price of the pumping watt cubic meter finally to give a price if you after sell it at the scale of a village, for example, or what's just okay. So now it's finished. If you have 1 kilowatt, you choose a panel on the market, and in order to be around 1 kilowatt, better to be a bit higher. Five panels will be okay, or 4 panels. So some examples you can find. We have seen that also here. Some PV like this with a tank, more simplest one, a bigger one, and for agriculture. Do you have any question? So it is the simplest solar design in terms of PV, because there is nothing else than PV panels. It's more difficult when you have other components to deal with. That's why we didn't spend too much time on this. You see just the principle to identify the need, then to make the link with energy, and then directly size the PV panels. Okay. I would like to spend more time on the tutorial I proposed to you. It's autonomous also, but including battery. Okay. So this is that. So, sorry, it's in French here. No, I made a mistake about the question. Okay. So it is a real also installation. This installation is combining wind turbine and solar PV. It is for a school in Burkina Faso. The principle is that, so it is a hybrid system, as we have seen, okay, and to have battery, then to use it. So the school is here. We will not consider that. Just focus on the PV, okay? So what I know, it is the place where it is. Okay, so I have the latitude, the longitude, two fundamental parameters, especially latitude, okay? I know also what is in this school, okay? So in this school, I have lighting, okay, light bulb inside the building. I have light bulb outside the building, so it is for the night to have light outside. There is inside ceiling fan, so air for comfort, refrigerator, and there is an office with a computer, radio, and photocopy machine. Okay. I know the power of each element. I know the number of each element. Okay. So the question that I will change that. I wrote in English, but so it should be in another way. What I have, but you can investigate in your side if you want to change. You can have a look, depending of the latitude, longitude, the place. You can see if you find other data regarding the radiation. Okay, but we have that has been established on a statistical approach of 22 years. So the monthly average insolation. So in January, February, so we see that the worst month is August here. Or we can have also idea of wind, but we will not consider wind. Okay. What else we have as data? We have some shortcut regarding the best inclination of the panels. It is the very simplest thing. If we want to design first roughly, it gives you an idea regarding the latitude for the best inclination we usually consider in order to produce the maximum of energy. Here, at the opposite of what I presented before, when I was speaking about facade and saying that we don't look at the maximum of production of energy because we want to be more close from the need, it is for connected to the grid. Okay? If we are connected to the grid, we can have another problem, another issue than producing the maximum. But for this kind of installation. It is autonomous installation. There is no discussion. The main issue is to produce the maximum. Okay. In my previous talk in the cities and so on, it is because I'm connected to the grid. So I want to produce not each time the maximum, but more close to the need. For this autonomous, of course, it is to produce the maximum. So these inclinations are giving, depending on the latitude, to produce the maximum, okay? The best inclination. And we have also some data regarding the battery that are available locally. But you can choose other battery if you find other battery, okay? But it's good to know also locally what are available technology. So there is lead battery and gel battery that are available. So this is data that you have. And sorry for this in French. The question is, of course, design the PV central. Design the storage, no, the battery. Select the material, so which PV panel we'll see for estimation of economic estimation, but and how they are connected. Okay, that means how many in series, how many in parallel. Okay, so first will be to identify the need, energy need, okay? Then what is the second thing to identify? Autonomy, okay? We want 1 week, we want 1 day. It's a huge impact for the battery, okay? And then design the PV, identify the model of PV, how you will connect them. Whatever the connection, you will have the same power, okay? So the problem is not to reach the electrical power you need, is how to connect them to have the same voltage with the battery also, okay? So you have to have a connection of PV, parallel series, then it will guide the inverter, and then it will also guide the way you will connect the battery. For sure, for such installation, they will have not one battery. They will have several batteries connected also. Okay? Is it clear as an objective? We didn't investigate the way to combine the battery. Alors, one battery. There is two characteristics for the battery. There is the voltage, okay? So could be 12 volt, for example. Okay. And the other characteristic of a battery, we have more investigate this characteristic, is the capacity. Okay, the capacity which is in ampere hour. So it could be, for example, 100. Okay. So if I'm doing that, what kind of connection is it? Series, okay? So what is the consequence as a voltage and capacity? It will be equivalent to a big battery, okay? And so what are the properties of this battery? Because when you are in series, the voltage are addition, okay? So it will be equivalent of battery of 24 with the same capacity. Okay, and so as a reverse, when you put some battery in parallel, okay, en parallèle, you will have a battery equivalence which is 12 and 200. So combining, it's like the PV modules. When you put the PV modules in series, the voltage are added. When it is in parallel, the voltage stays the same. Okay, but intensity is combined. So when you are in parallel, the voltage will stay the same, and in series, you are doubling the voltage and the capacity stays the same. So at the end, you will identify the number of battery to have your autonomy, but you will have to combine them, to connect them in order to be consistent with the PV field. So to go at the end of this tutorial, not to spend 1 week, we will make a rough assumption, of course, okay? But just to understand the way to design it. So for example, if I look at the battery, nominal voltage is 2 volts or 6 volts. So maybe, as I told you, PV modules is around 12 or 24 volts. For sure, we will not choose such a battery here. It's too small, we will have too much battery. So, depending, gel battery could be interesting and maybe more expensive, but you can choose. Or lead battery, probably at 6 volts, could be interesting and less expensive. But probably it's one of these to have a better connection, and it will depend of the voltage that we will have when we will plug our PV. But you see, if you want to have 24 volts or 48 volts, you will have to put the battery in series, and then depending of the intensity you want, add some rack in parallel. Okay. Don't know what time we have. 30? 30 minutes. Okay. So we can start. I can leave you think about that, and then I will. So first is to identify the energy need. Okay. So there is not too much. There is not too much device. So we have to decide. An important point is not sufficient like this. What information is missing? Time. Okay. So we have to make an assumption about time. So for sure the light during the night will not operate during the day. So it could be maybe 5 hours during the night. For the day, at what time the school is opening, at what time it's closing. Refrigerator, it could be continuous, 24 hours. Computer, so I have made the assumption that the lighting inside the building is 5 hours. During the night, it's 12 hours. For the comfort inside the building, it's 12 hours. Refrigerator, it's 8 hours, so that means that it will not operate constantly, but just when the people are coming at the school for them to put their dinner, for example, for lunchtime. Computer, radio set, photocopy machine, and maintenance could, if you want to put an electrical engine to make some thing, you need to think about that. So it's assumption, but it's up to you, if you are a designer, to discuss with your customer to see when the school will be open. What do you think? You think the refrigerator will operate all the day or just for your lunch, to the morning to keep your meal safe? The fan, and so this has to be established with discussion with the client. Okay. So we can go on this assumption to have the same data, if you agree. Another thing that is different regarding the lecture I give it to you, usually I stop at this to consider that is the energy that I have to provide and design it. As it is a school or something that could evolve, the number of children can increase. So in this case, it's not so stupid to measure this energy in terms of planning the future evolution of the school, because it's stupid if you just design for the needs today that you have to change your PV central or the connection because you don't plan that maybe the number of children will increase. It's not technically, it's not a problem to add some PV panels. What is the problem if you have your PV central that operate since 10 years, okay? And you want to add new panels, for sure they will be different. You have 80% of chance to don't find the panel that you bought 10 years ago. On the market, it will be disappeared because there are still improvement on new PV panels. So if you find the Voltec Solar 140 on the market and 10 years later, for sure you will not find this. You will find Voltec Solar 150 or 100 more efficient for the same surface. So you can, it's a problem after when you will plug to your existing PV central, because automatically you will generate a mismatch. They will have good panels that will operate very well and old panels that were aging together and working in the same configuration. So it's not so easy after to don't make disturbance on existing PV central if you are changing some panels. Because if you are changing, you are adding some more recent panels that are more efficient, so that will not operate like the neighbor. And I told you, if the neighbors are not operating the same way, it creates mismatch, and so it's not good for the whole PV central. Okay, so at the beginning you have at least also to think about future evolution, than to say, okay, if it's not enough, I will add some panels in 5 years. Because it's simple, yes, you can add some panels, but sometimes it's better to change every panels, so it has a cost, to operate in the same configuration than to add new one. Okay? It's the same if, for example, you have a PV central and one PV panel which is broken. If you change this one, it will operate differently because it's new, the efficiency is better, so it's induce mismatch. Okay. So it is also one advantage to add PV with micro inverter. You can avoid this problem of mismatch if you have all an installation with a micro inverter. So if you add a new one with a micro inverter, it will not disturb the other. Okay. So here I suggest to measure. So 30% is not negligible, but it's to be able to evolving in terms of needs inside. But this could be also discussed with the customer. Did your school in this area expect to grow in times? Do you have any idea of the number of children that will increase, and so on, to try to give you an evaluation for the sizing of your PV. Okay. The more difficult thing is to identify reasonably the needs. Okay. Here, so there is also two possibilities. I told you that we can also focus on the bad months, but here for the bad months it is holidays, the school is not working, so it is by discussion so that you know that. So it's a bit stupid to focus on this if the school is closed, okay? But otherwise, if it's operate all the time, you will choose that. So here what I said is that I choose a mean radiation. If I have a look here, which is not far from this value, which is 5 kilowatt hour per square meter or per day. But you can choose 4.84 if you want, okay? To be sure that focusing on that, you will oversize the PV installation, but here I have already oversized it, so but it is assumption. all is a question of the assumption you want to take. There is no bad assumption or good assumption. You are obliged to make some choice. Okay. So here, if you want, you can focus with your data on this. Okay, the bad months for the value. Okay, so I leave you to think about now a bit more. We have the energy, we have daily load, so we have the chosen what is the mean radiation factor that we will take. Do you have question? Okay, you have it. Okay. No, so in principle, you should be able to give me an evaluation of the power. So I have to choose a panel, okay? Now, what kind of panel? So what I suggest you is to take the same panel, so module, sorry, with a power. So it is Siemens solar module SP 104, 12. The power is P. Sorry. We can guess it is 140 watt peak. We can guess also the voltage. The reference is 104.12. The voltage is given by the voltage is 12 volt, and your useful voltage is 12 volt. Okay. But in reality, you can investigate different PV manufacturer to see the price or the power. So, but I suggest you to take this. So with a power peak of 140 and a voltage of 12. But you can find with the same surface, maybe 160. For sure it will be more expensive. And a voltage of 24. You can find also different voltage, 12 or 24. Usually it's 12 or 24. So now, thanks to this model, what are we able to identify, to estimate? Sorry? Yes, but so thanks to that, what are you able to determine thanks to this characteristic? You are able to evaluate the energy that one panel can produce for one day. Okay, thanks to that and that, you can have an estimation of the production of one panel. And when you have this estimation of production of one panel, compare to the global energy you need, it will help you to identify the number of panels. Okay? So I leave you, try to give me a number of panels. We can say one. It's a good. Yes, we will say for one. Somebody suggest a number. 70? More, I think. I found more, but maybe I made a mistake. We will check. Okay, so I estimate so that energy that could provide per day is 700 watt hour. The price that I found is for one panel is 129 euro. And so the number of PV panels is the global energy need divided by what one can produce. And you find 70? Me, but maybe I made a mistake. So check. So it is a global energy divided by 700. And check if you find the same. Maybe I've made a mistake because I done it.
Whenever we multiply, if we multiply 140 watt into that 5 kilowatt hour per meter square day, that multiplication gives watt square. So maybe there is a mistake.
Ah. Where?
At first startings.
Where?
140 into 5 into that area.
Yes.
First earlier slide.
So 140 multiplied by 5 kilo.
Kilowatt hour per meter square per day.
Yes. You don't find 700?
That numerical value we got 700, but the SI unit it is watt square.
Ah.
So I think
So
problem. Maybe division is there.
can you show me what?
This power is generated by one
Yes.
PV panel, and this is the what we got the
Yes.
kilowatt hour per meter square per day.
Ah, it is when you multiply.
Multiply then watt
Ah,
square.
no, yes.
Then maybe it is
But you have to multiply that by.
and area is 1 meter, no? So
Yes.
maybe this
I've got to check.
division.
5.
Otherwise this unit we need to check.
Yes. I've got to check. Yes. I will check for tomorrow. So, so compute, and we will. I will check for tomorrow. The other question I would like you look for tomorrow, so that we have the same energy produced for sure. I've got to check that. And the second, the next step will be to determine the number of modules in series and the number of string parallel. So maybe don't determine that for tomorrow, but think about how it could be determined, okay? And me, I will check that value. But so identify the energy produced by one modules and yes, and then think about how we will compute the number of modules in series, in one series, and then the number of string that you will put in parallel. The constraint is to be balanced. You can't imagine to put 3 modules in one string and 4 in the other in parallel. All the strings have the same number of modules. Okay, so if you choose 3 modules in series, then after all the strings that you will put in parallel will have 3 modules, not 2 here, 3 here. It has to be symmetrical and balanced. I give you also new data because depending on the power of the PV central, there is some advice regarding the voltage to have at the inlet outlet of your PV central. So for us, it will be so I found 84, but it will be a small PV central, which is between 2 kilowatt to 10. So we can select to have 48 volts at the born of the central.
Maybe here only sunshine hour you will need it.
Yes, but usually it's yes, you're right. I think it's a shortcut. I've got to check this result. Yes. I've got to check my value. Okay, so for tomorrow, check this value and think about how to determine the number of modules in parallel and the number of modules in one string, and so in series, and the number of string in parallel. And I will check my numbers. Okay. Do you have any question? So if you are not, we can stop here for today, and we will restart by this tomorrow. Okay. Thank you. And yes, think about that. So we'll assume that we will have 48 volts at the central born. Thank you.